Hooke's law. In the dynamics unit, we studied mechanical forces and their effects on a rigid, which means the object doesn't change shape or size, on its acceleration. In this unit, we will study how a non-rigid object changes shape or size under the action of applied forces. We're going to start with a mass m, right over here, which exerts an external force, mg, on this vertically suspended rod. There's the rod in the light blue there. The force stretches the rod, increasing its length by delta x. X sub 0 is the rod's original length. Delta x is the change in length, also called the elongation. And F is the force, or weight, exerted on the rod by the mass. Experiments show that there is a linear relationship between the elongation and the applied force when the elongation is small compared to the original length of the rod. This relationship is known as Hooke's law, after Robert Hooke, who first found it. So it's F is equal to K delta X. K is the elastic constant specific to the material being stretched. It is valid for almost any solid material, but it does have a limit. If the force is too large, the object may deform, stretching more than Hooke's law predicts, or even break. Let's work an example using Hooke's law. Find the elastic constant of a spring which elongates 0.26 meters when a 2 Newton weight is applied to the bottom of the spring. We write our givens right at the top here. We invoke Hooke's law, and we need to solve for k, so we'll divide both sides by delta x, and we get k is F over delta x, substitute in the givens, and we get k of 7.7 newtons per meter. Find the elongation of a spring with elastic constant 40 newtons per meter when a force of 32 newtons is applied. Here's the givens. And we want to find delta x this time. That's elongation. So we start with Hooke's law, solve that for delta x. And how do we do that? Divide both sides by k, substitute in our givens, and we get an elongation of 0.8 meters. Find the force applied to a spring with an elastic constant of 1.5 newtons per meter when its elongation is 4 meters. So here's our elongation, that's delta x, and here's the spring constant. We invoke Hooke's law, and this time we don't have to rearrange anything. We just put in our givens, we multiply them together, and we get a force of 6 newtons.